Now, if you're taking chemistry, you've probably seen some mole calculations. You may have seen dozens of different kinds. Here's what I want to show you today. There really only are two. There's only two kinds of mole calculations you need to worry about. The one that uses Avogadro's number and the one that uses molecular weight. That's it. Keep it simple. For instance, if I had some iron and I knew I had 2.5 moles, I can do this calculation. 2.5 moles of iron multiply by a unitary rate (1 mole of iron equals 55.8 grams of iron. My units of moles of iron cancel out. I have the unit of grams of iron left, and I get 139.5 grams of iron. That's one way I can use my mole calculations. I want to show you how these two different techniques can be used 6 different ways, very, very simply. First possibility is if you already have grams and you want to calculate how many moles you have. For instance, if I have 6.0 grams of hydrogen gas, how many moles do I have? Well, I'm simply going to divide by grams to cancel out those units and put moles in the top. I need an equality so that this ends up being a unitary rate, that I'm multiplying by 1. I know that 1 mole of hydrogen gas has a mass of 2.0 grams. So I'm simply going to divide both sides of that equation by 2 grams, and then use that unitary rate right there. 1 mole of hydrogen gas, 2 grams of hydrogen gas mean exactly the same thing. So this is equal to 1. I have functionally multiplied my original number by 1, which does not change the meaning. My grams of hydrogen gas cancel out and end up with 6/2 or 3.0 moles of hydrogen. That's my first type. The second type of mole calculation is if you have moles and you wish to get to grams. Simply the reverse of what we already did. So if I already know I have 2.5 moles of iron atoms, I'm simply going to get rid of the unit mole and get the unit gram. And I'm simply going to do that by developing the unitary rate that I did before. 1 mole of iron equals 55.8 grams of iron. And this time I'm going to divide by 1 mole. That gives me a unitary rate that once again I can use right here. If I have done the math correctly, my units have canceled out, I only have grams left, and the mass becomes 139.5 grams of iron. Now, if we're being careful and we say, I've only got 2 significant figures here, then I should report my answer as 1.4 times 10 to the 2 grams of iron. It has the same meaning as 2.5 moles of iron. That's the second type. Now, I hope you noticed that in both type 1 and type 2, all we used was the weights off the table, the atomic mass units, grams per mole. In type 3 and 4, we're now going to talk about particles and use Avogadro's number. If I have 1.8 times 10 to the 24th atoms of gold, and I want to convert that to moles. I need a relationship between 1 mole of gold and the number of atoms. That relationship is Avogadro's number. 6.02 times 10 to the 23rd atoms of gold. I already have atoms of gold, so I wish to get rid of that unit. So I'm going to divide both sides of my equation by Avogadro's number. This gives me a unitary rate that I can now use to calculate. For every 1 mole of gold, I need 6.02 times 10 to the 23rd atoms of gold. Once again, if we have set this up correctly, atoms cancel out, and the unit left is simply moles of gold. This will work out to be exactly 3.0 moles of gold. Again, 2 significant figures in my question, 2 significant figures in my answer. That's type 3. In type 4, I want to go from a known number of moles to a certain number of particles. Now, particles can mean several things. It could mean atoms, like we just did with atoms of gold. It could mean molecules or formula units. It could even mean ions. For now, we're going to stick to simple atoms. What if I had 4.0 moles of neon? And of course, neon does not form any compounds, so it's simply atoms of. I need to get rid of moles of neon, and I want atoms of neon. Again, I need an equality that is going to generate a unitary rate for me. 1 mole of neon atoms will be equal to Avogadro's number, 6.02 times 10 to the 23rd atoms of neon. I'm simply going to divide both sides of my equation by 1 mole of neon, and then use this unitary rate in my calculation. 6.02, 10 to the 23rd to 1 mole. Once again, my units must be set up correctly. Moles of neon cancel out, and I'm simply going to have atoms of neon as my answer. 2.4, 10 to the 24th atoms of neon. 2 significant figures in my question, 2 significant digits in my answer. That's type 4. Now, if you've successfully completed types 1, 2, 3, and 4, you have all the skills you need. All of them. Because in type 5 and 6, we're simply going to apply 2 at a time. Instead of going from grams to moles, I'm going to go from grams through moles to particles. We're going to do a 2-step reaction. So here's the setup. I've got 54.0 grams of water. How do I take that to particles? Well, I follow my units through. My first set of brackets, I'm going to put grams of water to get rid of that unit and go to moles of water. My second set of brackets, now that I have moles, I'm going to do exactly what I did in type 4. I'm going to go from moles to molecules of. I simply need 2 equalities to give me my 2 unitary rates here. Well, I know water. Water has 2 hydrogen atoms, one oxygen atom. That gives me a mass of 2, that gives me a mass of 16, a total mass of 18.0 grams per mole. That's my unitary rate that I'm going to use. 1 mole of water has a mass of 18.0 grams of water. Divide both sides of the equation by 18 grams of water. And use those numbers. 1, 18. My second set of brackets is exactly what we just did in type 4. 1 mole of water is Avogadro's number. 6.02, 10 to the 23rd, and now we're using the unit molecule of water. I'm going to divide both by 1 mole, and use the right-hand side as my unitary rate. 1 mole of water, 6.02 times 10 to the 23rd. Once again, if you follow your units through, grams cancel grams, moles cancel moles, and my unit left is molecules, which is what I was gunning for. If I take 54 and divide by 18, that's exactly 3. 3 times 6, that becomes 1.8 times 10 to the 24th molecules. And we have to put molecules of and the species, molecules of water. I would have to do the math on a calculator. I'm not sure if that's in 1.80 or 1.81, but I know I need 3 significant figures here because I had 3 significant figures when I started. If you look closely at type 5, you see it's really just type 1 and type 4 put together. It's not a new technique, it's not a new style, it's grams to moles, moles to particles. Those are the only 2 things you need. Grams to moles or moles to grams, moles to particles or particles to moles. You can do everything from that. Type 6 of mole calculations is particles to grams. And once again, we're not going to go directly particles to grams, we're going to go particles to moles, moles to grams. Again, we're only using 2 techniques. Avogadro's number to moles, moles back to mass using the periodic table. So in this example, I'm going to do 7.2 times 10 to the 24th molecules of oxygen. Molecules of O2. And I want to take this to mass. Well, my first step must be take it to moles. So I'm going to go from molecules of O2 to moles of O2. Once I've got moles, then I can go to mass and go for every 1 mole of oxygen, how many grams of oxygen do I have? A simple 2-step question. I need an equality. Well, from moles to molecules, I know that 1 mole of oxygen is equal to 6.02 times 10 to the 23rd molecules of O2. That's my equality. I can then divide both sides of any equality by the same number, which will be Avogadro's number. And use that as my unitary rate. And plug it in right there. 1 mole. And I didn't leave myself much room here, but 6.02, 10 to the 23rd molecules of oxygen. For my second set of brackets, I need a second equality. 1 mole of oxygen molecules is equal to 32.0 grams of oxygen. And of course I got the 32 simply by looking on the periodic table and seeing each oxygen atom has a mass of 16. Divide both sides of the equation now by 1 mole of oxygen. And use that unitary rate in there. 32 and 1. Again, my units should work out. Molecules of oxygen cancel molecules of oxygen. Moles of oxygen cancel moles of oxygen, and my unit left is grams. 7.2 times 10 to the 24th divided by Avogadro's number is about 12. 12 times 32. In this case, I did the math ahead of time, works out to be 382.7. 382.7 grams of oxygen gas. Once again, I come back here and go only two significant figures. So I have to stop there and go 3.8, 10 to the 2 grams of oxygen. And that would be my final answer. That's type 6. I want you to notice in all 6 types, all we did. We used the masses off the periodic table and divided by 1 mole. We used Avogadro's number and divided by 1 mole. Even in type 6, where it looks very complicated, it was simply moles to molecules, 1 in Avogadro's number. Grams to moles, number off the table, and 1 mole. Look back to all 6 examples. In every case, next to moles is 1. Next to moles is 1. Avogadro's number goes next to the particle. The masses goes next to grams. If you follow those simple 6 techniques, really only 2 techniques, you'll never have problems with mole calculations again. I hope this helps.